After a few consecutive wins, confidence surges, and decisions start to feel clearly right. When the next outcome reverses, the mind seeks a reason to shield the earlier narrative. This occurs because humans instinctively look for causes, even in random sequences. Vivid outcomes linger in memory, while less dramatic alternatives fade, making hindsight feel like evidence. This confusion fosters overconfidence in business, sports, and everyday judgments where luck often plays a dominant role. It also leads to unfair blame, as bad outcomes are often seen as personal failure, even when chance was the primary factor. A manager promotes the top performer after one quarter, believing the numbers reflect true talent rather than random noise. Another worker is harshly judged after an unlucky stretch, even though a longer record would show an ordinary performance. In the next minutes, you will learn how statistics, probability, and better framing can reduce these predictable mistakes. This video is inspired by The Drunkard's Walk by Leonard Mlodinow, and subscribe for more tools to think clearly about chance. The law of large numbers explains how results align with true probabilities as the number of observations grows sufficiently large. In simple terms, a fair process may appear biased in the short term, but stabilizes over many repetitions. Small samples can easily produce extreme patterns, so early data points often overstate both risk and opportunity. This is the law of small numbers trap, where one expects a small sample to perfectly mirror the entire population. A student flips a coin 10 times, sees 7 heads, and concludes the streak means something special. When the same experiment is repeated thousands of times, the proportion of heads approaches 1/2. Without considering sample size, random fluctuations are often misinterpreted as reliable signals. This mistake spreads quickly because quick conclusions feel satisfying and reduce the discomfort of uncertainty. When a claim is based on a few cases, ask what chance alone could plausibly produce such results. Then, seek longer records, repeat measurements, or aggregate data before treating a pattern as reliable information. The normal distribution is a bell-shaped pattern where most outcomes cluster near the average, with fewer appearing far away. Standard deviation measures the spread of this bell, indicating how wide typical variation is around the mean. Understanding the spread helps distinguish ordinary fluctuations from truly rare outliers that require special attention. Without this context, a single performance number might feel decisive, but it can shift widely when repeated. A chart can rank hundreds of fund managers by 5-year returns, and the curve invites explanations. When the same managers are tracked in the next period, rankings often dissolve and outcomes resemble noise. Regression toward the mean is the tendency for extreme results to be followed by results closer to the average. This tendency explains why a record year, or terrible year, often fades, even when observers expect a continuation. Compare multiple periods, look for consistency across conditions, and ask whether changes exceed typical variance. This approach prevents rewarding or punishing people for extremes that were likely to soften with more data. Heuristics are quick mental shortcuts that simplify uncertainty, but they can distort probability judgment. One such distortion is the assumption that a story fitting expectations must be more likely than a simpler alternative. Adding extra details makes a scenario feel more realistic, even though each uncertain detail actually lowers the probability. This can create the conjunction fallacy, where a combined claim is rated as more likely than one of its parts. Someone might read a vivid profile and confidently select the more detailed option as the probable description. The more detailed option can still be less likely, because it requires multiple conditions to be true. Once a belief forms, attention tends to hunt for confirming cases and ignore quiet counterexamples that would weaken certainty. The result is overconfidence in explanations and an underestimation of how often similar patterns arise by chance. Separate story appeal from probability, then ask what evidence would actually change the conclusion. Subscribe if you want more clear tools for spotting these shortcuts and replacing them with sound probability habits. Conditional probability seeks to determine how likely evidence is given a specific condition, which is different from the reverse direction. Mixing up these directions can lead to the prosecutor's fallacy, transforming a mere match into a claim of near certainty. Base rates are crucial because when an event is rare, false positives can outnumber true positives. Error rates also matter, as even careful tests and expert processes can occasionally produce incorrect results. Consider a medical screening where the test is accurate, but the condition is uncommon in the population. Many positive results can still be false alarms, as the pool of healthy individuals is much larger. The key lesson is that certainty depends on context, not just on a dramatic statistic. Numbers that ignore base rates hide uncertainty behind an appearance of precision that can feel persuasive. When you hear a 1 in a million figure, ask which probability it represents and what group defines it. Always demand the full chain from base rate to test accuracy to final probability before accepting a confident conclusion. A random walk is a process where each step is unpredictable, but the overall path still has statistical structure. Small random pushes accumulate, so two paths that begin similarly can diverge dramatically after many steps. In careers, chance encounters and timing can open doors, and later success then appears as a result of pure intention. Another person with similar preparation can miss the opening and never reach the stage where skill becomes visible. Complex systems also produce failures through ordinary interactions, so accidents can occur without one dramatic trigger. When components are closely connected, small glitches can cascade, and hindsight often invents a simple cause. The lesson is not pessimism but humility about prediction and a focus on safeguards under uncertainty. This mindset favours redundancy, diverse options, and plans that do not depend on one lucky break. Build systems that survive bad luck by using buffers, spreading exposure, and avoiding single points of failure. Judge performance across long periods and many peers, so luck is not confused with mastery. A calmer approach starts by accepting uncertainty as a built-in feature of the systems you depend on. Once chance is acknowledged, outcomes stop feeling like moral verdicts and start looking like signals mixed with noise. Large samples reduce volatility, distributions map what is typical, and regression warns that extremes usually soften. Heuristics create seductive stories, while conditional probability keeps base rates and errors visible in decisions. These tools reduce overreaction, as fewer choices get driven by one surprising week or one headline. They also encourage fairer judgment, since performance is evaluated over time and within realistic statistical limits. Begin by finding one area where short streaks have been treated as proof, then widen the time window. Next, write the base rate, the sample size, and the possible errors beside any statistic you plan to use. With that habit, uncertainty becomes manageable information, and choices become steadier even when outcomes stay unpredictable. Subscribe if you want ongoing guidance for separating luck from skill and building clearer judgment under uncertainty.